Hi, this is Daniel, and the paper I read was on integrating cluster formation and cluster evaluation into interactive visual analysis. So what that means is it shows a visual way of how you both create the clusters and then evaluate the clusters. So what is visual cluster analysis? The paper defines it as an interactive framework for determining a cluster based off its tendency, which is the non-random structures, meaning things are clustered together for a reason and they're not randomly clustered together, and then comparing between clusterings. So if you run a clustering algorithm with one set of parameters versus another, like how many clusters, what your distance function is, and so on. The stability of those clusters, meaning the consistency of them. If you cluster based off different like number of clusters or different distance functions, the similar data will always cluster together. And then cohesion, how closely related the data items within the cluster are. Okay, so traditional visual clusterization or visualization of clusters is usually things like scatter plots like this, where you have your set of data in a 2D model here, and then you kind of just circle them in different colors showing the different clusters. And then you can see in this example you create two different clusterings, B and C, and then you use them to determine D, and you kind of has these arrows determining that this cluster comes from here, this cluster comes from B, and then C, they actually had to remove a few points because they weren't as coherent in the cluster. So they have this cycle they talk about in the paper where you start forming your clusters, and you do this by what's called a difference matrix, and then you create your clusters. And then once you create your clusters, you then evaluate them with that dissimilarity matrix and parallel clustering model, and then you'd use that to then potentially tweak your clustering algorithm, whether it's the distance function or the number of clusters, and then you can go back and create another clustering and then continue this cycle until you have your final set of clusters. So the dissimilarity matrix that they use for visualization, it shows the distances between your data points. So you have your data points on your x and y axis here, and here's a little example where the more related they are, the more red or the higher similarity they have. So you can see in these examples where you start to form similarities in certain areas of the clustering, and then you can use this before for your clustering itself to kind of know where your clusters are going to be. And then you can look at it more detailed for creating your clusterings, where you can see where this area of data is more similar, and then here, and then here, and then you can create your 5 clusters from this data here. And then the other view they have is parallel clustering view, where you can see where the data flows to for each clustering. So if you have a good clustering like this example here, your data will flow and be in the same cluster in every single clustering. So you have 3 different clusterings here. Or your data can flow between multiple clusters, like here, where one cluster gets spread apart into 2 and 3 and then flows back together. So the paper talks about using these together to show how good your clustering is and which clusters are the strongest. So you can see here in C0, the cluster actually breaks apart and then forms multiple clusters, or goes into multiple clusters and then further goes into another cluster. And you can see based off the dissimilarity matrix that you don't have too strong of a similarity in certain areas versus this cluster, which stays in the same cluster every single time it goes through the different clusterings. And then you can see that here based off of the differential matrix, or the similarity matrix, sorry. So they give a good example of how this is useful in practice with this example in biology of lipids and how they move. So they have different clusterings based off different time intervals. So at time interval 100, they notice that these lipids are far away from each other, and then as time goes on, they actually come together and form a cluster. And then later on, at the end of their time interval, they actually spread apart again. So you can see that how the data flows through your different clusterings. And that's about it. The paper is mainly about visualizing how your clusters are, or how your data is flowing through your clusters, where they're getting clustered, and then you can use that to change up your clustering, find out where it's being weak, find out where it's strong, what you need to change, maybe your weights, how many clusters you have. And yeah, that's about it.